Hello, this is the second part of the marking scheme for the exam taken on 27th May 2021 for Electrical Principles module. Questions number 7 and 8. Question number 7 is asking about creating or drawing the Thevenin equivalent circuit of the rest of a network where the load is indicated in the question. We remove the load here. But here the method is specified, that is successive conversions of Thevenin-Norton equivalent circuits. Sometimes there is no indication of a method, so feel free to apply any methods you like. Especially you can go through the 4-step method we have in the slides, in the lecture notes. But here we need to convert Thevenin to Norton, Norton to Thevenin to reduce the network. I don't have the original one. You have it in the original exam paper. There you see there are two Thevenin models. Basically, Thevenin model has the voltage source connected in series with resistance. Here you see the conversion, the converted versions to Norton. This is for the first part. You had in the original one 15 volt and 5 ohm. So this is going to be 15 divided by 3 amp current source and 5 ohm resistance. The other one was 10 volt and 5 ohm. So 10 divided by 5, voltage divided by resistance, it gets you, gives you the current, 2 amp. So this is the current, and you copy exactly the same resistance here, but this time parallel. Of course, in Norton, a current source is connected in parallel to a resistance. Next step, we say, okay, there are two current sources, both of them are injecting current to this node, so we can replace those two current sources with a single current source, 5 amp, because 3 plus 2 equals 5. And we see also these two resistors connected in parallel, they are equal, we can replace them by half of them, 2.5. The rest of the network we keep as it is. Next step is we convert this Norton-like equivalent circuit to its Thevenin equivalent one. So we need to replace the current source with voltage source. The value of this voltage equals this current multiplied by this resistance. So 5 times 2.5 equals 12.5 volt. Resistance or resistor remains unchanged. The only difference here is you need to connect it in series to the voltage source. Now, if you look at this Thevenin and this Thevenin, you see it's like there are two voltage sources or two batteries connected in series. The polarities are the same. This is injecting current clockwise. This is also injecting clockwise. We can add them. So the total voltage source here you can put is 12.5 plus 2.5, which equals 15 volt. And about the resistors, this resistor and this resistor, they are series. So 2.5 plus 4, which is 6.5, is the total resistor you can put there. And this is the equivalent part we made. The remaining is the parallel branch here. Now, if we convert this part to Norton, then we see this and this. If this is also converted to Norton, then we will have 2 or 4 basically parallel branches. Conversion of this one to Norton is, okay, you divide the voltage source by this resistance, 15 divided by 6.5, which is 2.31 amp. 6.5 ohm resistance is copied here. You only need to make it parallel. For this part, 6 divided by 2 is 3 amp. And 2 ohm is here, just parallel. So this is the Norton for this Thevenin, and this is the Norton of this Thevenin. Next step is, again, there are two current sources parallel. Both of them are injecting current to this one, so you add the currents to have the total current. 2.31 plus 3 equals 5.31. And there are two parallel resistors. You can calculate the equivalent one. Multiply them and then divide by sum. You get 1.53 ohm. So this is your final Thevenin model. Voltage source and the resistance, VTH and RTH. Now we can reattach the load to do the calculations requested in the question. The calculation needed is the voltage drop of the load. So this is my load, 7 ohm load, and this is the equivalent Thevenin model. So this is like the new circuit you need to work out. In order to find this voltage, there are two ways. One is you calculate the total current here by simply dividing total voltage by total resistance. And once you've got the current, you multiply by this resistance. That is the voltage here. The second way is voltage divider rule. So total voltage multiplied by this resistance divided by the sum of the two resistances. And this is the voltage drop of the load. Part B is about power. These are the general formulation you need for power. I should say the only one you need to know is the definition of power in electrical systems. Electrical power equals multiplication of voltage and current. Then, sometimes you may not have current. So in that case, this current can be replaced by V over R based on Ohm's law. And this gives you V squared over R. So if you remember this one, you can quickly apply this one. If you don't remember this one and you only know the definition of power, first you need to calculate current using Ohm's law and then use this one. The other formula that I'm sure you know is this one, Ri squared. This is again based on the main definition of power. The only difference here is you replace voltage by multiplication of R and I, Ri. So then that is Ri squared. In this case, we are asked to calculate the power of this load. So we know the voltage drop of the load and we know the resistance of the load. We are not interested in the current of the load. So we can quickly apply this formulation to obtain power. In the continuation of this section, we're asked to calculate the maximum power dissipation. Maximum power here happens when this load has a resistance equal to 1.53. This case. So only in this case, power here is maximized. So what is that power? In order to find this power, I can firstly calculate current in this new circuit. It is new because we replaced the old load with this new one, 1.53. So you can calculate the total load and then you apply this formulation to calculate power. Power equals Ri squared, nu I and nu R. So you get 10.77 watt as the total power, and this power is maximized. If you compare this with the previous one, which was 6.34, this is more. Question number 8 is a circuit. The first question is how many principal nodes and how many principal loops you can identify in this circuit. There are two principal nodes. This is not a principal node because these two resistors can be merged and basically you have a single resistance and a branch here. So there is no principal node here. Here, there is no principal node because if you swap these two devices, the voltage here is known, that is 25. The same for here. The voltage here is known, is 50. If you say this is my reference node, then this voltage is 50 volt because this battery is a 50 volt battery. So this cannot be a principal node. There are only two principal nodes. What about principal loops? I can identify 3 principal loops in this system for mesh method. So in summary, you need to write there are 2 principal nodes, 3 principal loops. So if we go for nodal method, there will be 2 equations, 2 variables in the end, and that means it generates fewer number of equation variables. So nodal method outperforms the mesh method here in terms of the performance. But in the end, applying mesh and nodal method will give the same results. That's why in section B we say regardless to what you answer to section A, choose one of these 2 methods and solve this circuit. Obviously, if you go for nodal method, you get the answers faster because you need to deal with 2 equation, 2 variable problem. One way is to start with writing KCL and then go to matrix way or elimination method. The other way is generating these matrices quickly and then continue with the rest of calculation. So I'm just putting this paper here to show how we're forming these matrices. So you need a 2x2 matrix because there are two principal nodes. You need this vector with two elements and a vector of current sources. So when we say current, so this needs to be ampere, okay? For the first node, this node, total current injected to this node by the current sources is the one coming from here, and that is 25 divided by 5. And for the node 2, that constant current is being injected from this branch, and that is 50 divided by 2, 50 divided by 2. These are my variables in the nodal method, and here I form the coefficient matrices or impedance, conductance matrices actually. So in this matrix we have diagonal and non-diagonal elements. For diagonal elements, which is like 1 1 or 2 2 cell, for 1 1 you need to look at all the conductances connected to node 1. One of them is from here, so resistance is 2 ohm. You need to put 1 over 2. From this branch, resistance is 5 ohm. You need to put 1 over 5. And here it's 10 ohm. You put 1 over 10 Siemens. That is actually the conductance. For node 2, from this branch, 1 over 2, 1 over 4, and 1 over 10. So 10, 1 over 4, plus 1 over 2. For the non-diagonal elements, which are conductances between two nodes, this one is between node 1 and 2. So 1 and 2, there is 10 ohm resistance. You need to put the inverse, which is 1 over 10. And be careful, don't forget to put these negative signs for the non-diagonal elements. And the matrix is a symmetrical matrix, so non-diagonal elements for the same nodes are the same because this is a bidirectional network. Then obviously we need to solve this. The first step, we can just convert them to decimals to better calculate the determinates. When you go to the determinates, you know the way to use determinates, you don't have to obtain both variables v1 and v2. You only need v2 because in the question we are asked to calculate a current flowing through a 4 ohm resistance. And if you look at the original question, you see to obtain that current, this current, you only need to know v2. So you can just write this part, okay? And this part below, you put the determinant of this coefficient matrix, and on top, you copy the same, and you only replace the second column, because this is second variable, okay? Second column by the current sources, current values. And you obtain the determinant, you get 30.6 volts, your V2. And now if you divide it by that 4 ohm resistance, you get the voltage, the current flowing through that resistance. And this was the end of this exam paper.